Hi.
Hi, are you sure this course is just for 2499?
Yes, and you know this is the only course with this expertise across the world.
No way!
Yes way. Don't delay. Enroll now.
Geeks learning together.
Hi.
Hi, are you sure you can prepare for product based companies through this course?
Yes, sitting at home?
No way!
Yes way. Don't delay. Enroll now.
Geeks learning together.
Yeah, so hello everyone. So, how many people are there in the chat? So, can you please mention your name in the chats to mark your presence so that we can begin? Hello, SK. SK, are you there right now? And one more thing, kindly mention in the chat box that I am properly audible and visible so that we can quickly start. Okay, so let me just wait a few minutes for other students to join and then we will start. Okay, and if you have joined the stream today, kindly write your name in the chat box to confirm your presence and then we can start. So, hello Miral, how are you? So, Miral, is this your first session today? Okay, okay, thank you. Thank you, SK. So, SK, is this your first session today? And same for Miral as well. So, I am sharing my screen. I hope the screen of Google Jamboard is perfectly visible to everyone. I have changed the background as well. So, let me change the. Okay, Miral. So, thanks a lot for your for staying with me in these sessions. And so today the topics, as you can see, we will be discussing about bipartite graphs and topological sorting. Okay. And SK was asking that do we need to know DFS and BFS or we can directly watch this live? Actually, you should know DFS and BFS because those are the basic traversal algorithm, and we will use them to solve bipartite graph and topological sorting both. Okay, both can be solved by both of these algorithms. Okay, and and actually I have covered these topics in my previous sessions as well. Today is the sixth session. We already had five sessions previously, so the recordings are already available there. Okay, so you can watch. Okay, so let us start then. So, a very good evening to everyone. So, today is the sixth session of this graph and tree series for your interview preparations. So, basically, let me give you a brief introduction about the series. This series will go on for the entire month of December and up to the first week of January. And we will be covering most of the important concepts related to graphs and trees, which are asked which are commonly asked in interviews. Okay, and we will be discussing questions as well. I will be giving you homeworks as well, and the link of this slides are already present in the description of this video. Okay, so previously we have already discussed topics like representation, how graphs are represented. Then we have discussed about DFS, we have discussed about BFS, we also have discussed about connected components as well. Okay, apart from that, we have discussed about um, what else did we discuss? We discussed about multi-source BFS. We discussed about multi-source BFS. We discussed also about 01 BFS, and we discussed a few problems as well. So today is the day for bipartite graph and topological sorting. So, so do you all already know about bipartite graph and topological sorting? Can you please write in the chat box? Yeah. So before we begin, so let me give you a Yeah. So before we begin, let me give you a small introduction about myself. My name is Gourav Kumar Shaw, and I am presently in my third year at IIT Kharagpur. Yeah. So right now, presently, I'm in my third year at IIT Kharagpur. I'm a mentor at Geeks for Geeks, and I'm also an incoming software engineering intern at CureFit. Okay, so let us begin with the topics then. So I would request everyone who have joined with me to kindly stay in the session till the very end. So I will be discussing three or four very important concepts today. Okay, which are very frequently asked in interviews. And one more thing, during my campus internship placements, internships drive. So basically, I was asked a question related to topological sorting during my interviews. Okay, so as you can see, these are very frequently asked in the interviews as well. So let's begin then. So the first and the most important point here is to know the definition of bipartite graph. So, so the definition of bipartite graph is that it is if it is possible to color the nodes of our graph with two colors such that no two colors are adjacent to each other. Okay, so by the help of this definition, we can understand what exactly a bipartite graph is. So what is this saying? Let us see. So it is saying that let's say we have a graph with various nodes. Okay, so let's say we have a graph with various nodes. Now somehow we have been asked that we have to color each of our nodes with only two colors, and those two colors can be anything. Let's say red and let's say black. Okay, so we can color our nodes in only two colors, and we have to color in such a way that no two adjacent nodes are of the same color. Okay, so let us start coloring them. So let me say that I am marking the first node as black. So the next node should be marked as red. After that, I will be marking as black. Okay, so I have to mark this one as red. Okay, so since I am marking this one as red, I will mark these two as black and this one as red. Okay, so since I am marking this as red, I will not mark, I will be marking this as black. Okay, but now the most important thing here is that we see a point, this part in which both the adjacent nodes are black. Okay, so therefore this is not a bipartite graph. This is not a bipartite graph because we are not able to color all the nodes in such a way such that no two nodes are of same color when we are trying to color with two given nodes. Okay, so any doubts here? I hope not. So this is kind of a definition which will help us to understand the concept of bipartite, but this is not the formal definition. The formal definition is something like this. Yeah. So the formal definition is something like that. It says that if we have been given n nodes, let's say, let me add a new page here. Yeah. Yeah. So the formal definition says that let's say we have been given n nodes. We have been given n nodes, and basically we have to divide all those n nodes into two parts. Okay. So let's say we have been given n nodes, and our task is to divide them into two parts, two sets, or we can say, okay, two sets, such that basically I can map each node present in one set to a different node present in this set. Okay, so I can, if I'm able to possibly make it in this fashion, then I can say that those are bipartite graph. Okay, this is the Wikipedia definition of bipartite graph. Okay, mathematical definition. Okay, but understanding the definition, as I've just told in the previous part, that we have to make sure that we are able to color all the nodes in such a way that such that no two adjacent nodes are of same color. Okay, that is a kind of an important definition, and we should know that. Okay, so the question arises: can we make a bipartite graph, and how to make a how to identify a bipartite graph? Okay, so does anyone know how can we identify a bipartite graph? Hello, Miral. Hello, SK. Yeah, I would request everyone to kindly uh, interact with me in the chat box so that it will help me also to deliver content in a much better way. Okay. So yeah, so the concept here lies, one more thing I have to say, that no, a few observations that we should make regarding bipartite graph. So what are the observations? First of all, let me draw a graph. Okay, the graph that I drew previously, it was not a bipartite graph. So can you tell me why this is not a bipartite graph? This graph was not a bipartite graph. This was not a bipartite graph because when we were trying to color, we got two nodes which were of the same color. But one more observation we can say, that we also encountered a cycle, and the reason that we are able to find two nodes which are of which are of same color, it is because there was a cycle inside the graph, and more importantly, it was a cycle of odd length. Okay, as you can see, 1, 2, 3, 4, 5. So it was cycle of odd length. Now we can very safely assume that if there is any cycle of odd length, it means that it will be not a bipartite graph. Not a bipartite graph. Okay. But let's say if there was an even length cycle, let me just introduce one more node here. Let me introduce one more node here. Okay. In this case, what I can do, I can easily color this node with red. Okay, if I'm doing this, then what will happen? Basically, this is a bipartite graph now. This, yes, it is a bipartite graph. Why? Because there was an even cycle node. So what observation can we draw from this thing? Can anyone tell me? What observation can we draw from this? The observation that we can draw is that if there is a odd cycle, if there is a odd length cycle, odd length cycle in a graph, then it will not be a bipartite graph. Okay, and else, yes, it will be a bipartite graph. Yes, it will be a bipartite graph. Okay. Now, if there is not a odd length cycle, it doesn't mean that there has to be an even length cycle. Okay. Even if there is no even length cycle, there is no cycle only, then also it will be a bipartite graph. Doesn't matter if it is an even length or there is no cycle. Okay. For example, if I am drawing a graph of just a very straight graph, okay. So this can be, let's say I'm coloring this blue, this is red, this is blue, this is red, and this is blue. So as you can see, all the pairs are basically different. Okay, all the adjacent nodes are of different color. So therefore, we can say that this straight graph is also a bipartite graph. So all we have to make sure that there are no odd length cycle. If there are an odd length cycle, it will not be a bipartite graph, else it will be a bipartite graph. So this was the observation that we make. Okay. Now sometimes this kind of observation will help you to solve a hard level questions. Okay. So now let's look into an algorithm. So the question says we have been given a graph. We have been given a graph. Now our task is to basically identify whether this graph is a bipartite graph or not. Okay. Now how we will do that? Okay. Can anyone tell me? Can anyone just write a small brief description of how can we basically do this? That how can we identify whether a graph is bipartite or not? Okay, can you just meanwhile I am just opening my opening the GFG problem link. Okay, give me 2 minutes, please. Let me open the GFG problem link of this question so that we can. So meanwhile, you can type in the chat box. Okay, what exactly are you all thinking? Okay, and meanwhile, let me open the. Okay, so Sumit is saying that we will be doing a BFS. Okay, yes, we will be doing a BFS, but let's. Can you tell me the concept exactly? What exactly will be your checking condition while we are doing BFS? Uh, okay, I'm really sorry. I just my mic was muted and I could not see that. So let me just repeat it once again. Okay. Sorry, a mistake on my behalf. So, okay. So anyway, what I was trying to explain here is that we will be using the BFS algorithm. So, Sumit, can you tell me at what point of time did I got muted? Like which part I was explaining and I became inaudible. So we'll start from that. Or let me just explain the whole part only. Again, it will just take a few minutes. So what I was trying to say here is that we will be using the BFS algorithm. Okay. So if we are using the BFS algorithm, it means that this BFS algorithm traverses in a level-wise fashion. Okay. So what does level-wise fashion means? That once a node is inside a queue and we are processing that node, it will try to process its neighboring node. Okay. Now this is the condition we need. We need to check whether the neighboring node is colored as same as the colored the same or not as its neighboring node. Okay. So what we will do initially, we will maintain a color array because we need to check whether they are of the same color or not. So initially what we are doing, we are basically putting all the values as -1 inside our color array. So -1 basically indicates that those nodes are not yet visited and we haven't colored anything in those nodes. Okay. Now there are two colors. Okay, the concept of bipartite involves two colors. So let me take the first color to be 0 and the next second color to be 1. Let us denote 0 by black and 1 by white. It doesn't matter. Okay. The thing is both are different color. So we will start from any given node. Okay, let's say 1 we start and we give it any color. Let's say we give it a color 0 and we simultaneously update in the color array as well. We now push it into the queue and after the queue you take it from the queue and process it. Now once we are processing the node number 1, we have to go to its neighbor, which is node number 2. Now once we go to its any neighbor, first we will check whether it has been visited or not. If it has not been visited, in that case we will visit that array and allot it a color which is of the opposite color of the initial node. So in this case 2 has not been visited. So I will allot a color opposite to the color of 1. So I will allot color of 2 as equal to 1. Okay, so basically, okay, thank you, Sumit. From start of this slide, I'm explaining. Yeah. So basically, what will happen now here is that it will basically allot a color of the opposite nature. Now again, it will come to it will push the slide code node number 2 into the queue. Now again, node number 2 will be processed and the same thing will get repeated. But if at any point of time, a given node, basically say a given node is while we are traversing the given node and we see that node has already been colored. Okay, it means that there was a BFS from some other path which had basically colored that node. Okay, then we will check whether the node which has been colored is the same as the current node or not. If both the node are colored are same, in that case we will return false. Okay, just for example, when it will come to 2, it will mark it as 1. Now from 2, it will go to 3 and 6. So it will mark these as 0. Okay, from 3 it will come to 4 and it will mark this as 1. 6 will come to 5 and it will mark this as 1. From 4 it will go to 7 and mark at 0. But when 4 will come at 5, so basically when 4 will come at 5, this part, when 4 will come at 5, it will see that both the colors are same. It means that someone came to 5 and marked it as 1. Okay, and since both the color are same, it is not a bipartite graph and we will return false. And if during the entire BFS there was no point of time in which when we return false, it means that this is a bipartite graph. And finally we will return true. Okay, so this is the concept of how we are going to apply BFS to solve the problem. Okay, I hope everyone understood it. Sumit, did you understood the concept of BFS? So let us solve this question in GFG ID. Yeah. So this is the IDE of Geeks for Geeks, and I will try to solve this question here. So whatever I have just described, I will be implementing that only. Okay. And one more thing that we have to basically make sure is that the concept of connected components. Okay, so what will happen here is that if there are n nodes, now it may happen that some of the nodes are not connected, that all the nodes are not in a connected component, in a single connected component. So therefore what we have to do is we have to make sure, yeah, so what we have to do is that we have to make sure that we are running our loop for all the connected components. Okay. Okay, yeah. So initially what we are doing, we are declaring a color variable. After we are declaring a color variable, we are basically putting all the values as -1 inside our color variable. Okay. And we have to start from index number 0 because in the question it is given that our nodes is 0 based index. After that, what we will do, we will check. We will run across all the nodes and we will check whether they are colored or not. If they are not colored, in that case, what we will do, we will call the BFS function. So this check is nothing but a BFS function which we will implement later. And if this check function is returning false, we will return false because it is not a bipartite graph. And if it is not returning false at during any of one of the time, in that case, we will return true. A graph is not is a bipartite only when all of its connected component are bipartite. Okay, it may happen that one of its component is bipartite and the next one is not bipartite. So in that case, entire graph becomes a non-bipartite graph. Okay, that is the concept. So that is the reason we are basically checking if they are false or not. If they are false, we will return false. If it is true, doesn't matter, let it be. If it is true for all the nodes, then we will return true. Okay. So now it's time to implement the check function. Check function is basically an implementation of the breadth first search to solve this problem. So let us solve this problem then. Okay. So are you all with me? So SK was saying that he wanted. SK, are you there? Anyway, so let us continue. So this was a check function which I just described. So this is an implementation of the BFS. The first and the most important thing what happens in BFS is the starting node. Okay. So we are taking this variable as a starting node and we are passing all of the nodes one by one in case if it is not visited. Okay, so now we see that basically we have to declare a queue variable, queue data structure. Inside the queue, we will push the start element of our starting node. Okay, and at the same time, we will color it as 0 because it is a starting node, so we can color it with 0. Let us say because we can color it with anyone. The idea is that if we're coloring it with 0, we have to basically color the next adjacent node of the opposite nature. So now we will run a while loop. This traditional, this standard while loop of BFS. We will take the front node from our queue and we'll pop that. Now it's time to explore this point. Okay. Now this for loop will go across all the levels, all the nodes which are at a present level 1 greater than the current node. That it's all its adjacent node. And how can we do that? We can do that by writing for auto IT adjacent of node. Yeah, so we can write auto IT adjacent of node. So what will happen in this case is that, yeah, so if the adjacent node is not yet colored, first we will check whether it is colored or not. If it is not yet colored, in that case what we will do, we will color it. And how we will color it? We will write color of IT is equal to exclamation mark color of node. This is basically a not operator, which will basically put that value. If it is 0, it will put 1, and if it is 1, it will put 0. So this is how we are making sure that an opposite color is basically assigned to any particular node, or any particular neighboring node. And since we are assigning a color, we have to push it in the queue as well for it to get processed later. Okay, now after this is done, we have to put an else condition as well. Now this else condition will check whether the color is same or not. If it is same, so if at any point of time we are encountering two nodes which have the same color, in that case what we will do, two adjacent nodes, we will just return false directly. And if during the entire BFS algorithm, if we did not encounter false at any point of time, we will just return true in that case. Okay, so I hope everyone got it. So let me just submit this problem and check whether it is correct or not so that we can move to the next part. So can I have a +1 in the chat? Sumit, did you understood it? So we have 4 people with me right now. So did you all understood the concept of how we are applying the BFS traversal to solve this problem? And yeah, one more thing is that, thank you, Sumit. Yeah, one more thing here is that yeah, we see that all the test cases have passed, so therefore it is correct. So the few important concepts here is that the color array will be initially marked as -1, and we have to do this BFS traversal for every component. So that is the reason we are putting it this. Now it may happen that let's say we are just putting basically if we let's say we consider to start from node number 0, okay, then in that case we will get a wrong answer because it is not given in the graph that we have been given one single connected component. Okay, so we are not supposed to assume that. Okay, so this question is done. So let's move to the next question. Now the next concept is basically topological sorting. Okay, so let us see how. Yeah, so this is topological sorting. Does anyone have any idea what exactly is topological sorting? Any idea what exactly is topological sorting? Hello. Okay, Sumit. That's great that you know about it. So let us do one more thing here is that yeah. So let us look into the concept of topological sorting. Now, according to the definition of topological sort, what is it? We have to basically linearly order all the nodes of our given graph. The definition says that it is a linear ordering of vertices such that if there is an edge between u and v, u appears before v in that ordering. Okay, so it means that we have to write some sort of ordering of our all the nodes of our graphs in such a way if there is a directed edge from two nodes u and v, in that ordering u will always appear somewhere before v. Not necessarily that u should appear just immediately before v, but it should appear somewhere before v, okay, in our final ordering. So this is how we have to proceed. Okay. Now, for example, let's say this is a valid toposort of this given graph. The given graph is something like this. So we see that 542310 is a valid toposort. So 542310 is a valid toposort. Let's see how. We see that 5 is present before 0. 5 is connected to 0, so 5 is present before 0. And we see 5 is present before 0 in our order as well. We see that 2 is connected to 3. So 2 should become before 3. Yes, 2 is before 3. We see that 4 is connected to 1. Okay, so 4 is present before 1 as well. We see that 3 is present connected to 1. So 3 is also present before 1. So we see that the condition, yeah. So basically we see that the condition for topo sort is basically satisfied by this order and by this order as well. Okay, now if we are considering this order, we can see that 4 is present before 1, 4 is connected to 1, 5 is present before 0, 5 is present before 0, 2 is present before 3, 2 is present before 3, 3 is present before 1. So basically these two orders are correct topological sorting order. So that brings me to the most important point here is that we can have multiple valid topological sort. So Sumit is saying that nodes with 0 in degrees come first than others. Yes, Sumit, that is the when we will discuss about Khan's algorithm. Okay. So, but before doing Khan's algorithm, I will basically show you how exactly we can do using depth first search as well. Okay. So, so let's talk about the theory first. Okay. Now the question is that topological sorting can only be applied to directed acyclic graph, okay, which are also called DAGs. So why it should be directed and why it should be acyclic? Can anyone tell me? Sumit, can you tell me why it should be directed and why it should be acyclic? Anyone other than Sumit as well? Hello, Dil Hyder Studios. Are you there? Yeah. So let me tell you why. Basically, so it should be directed because according to the definition, u has to be directed to v. Then only we are placing u as v. If suppose it was not directed, what will happen? We are writing u and v as an undirected graph. In that case, do you know what will happen? Since u is connected to v and v is connected to v, it means that u should come before v and v should come before u. So it is that this doesn't make any sense. So therefore, we will say that it should be a directed graph. And why a cyclic graph? Because if there is any cycle inside our graph, okay, uh, uh, yeah. So let's say if there was any cycle inside our graph, let's say 1 is this, 2 is this, 3 is this. So 1 is connected to 2, 2 is connected to 3, and 3 is connected to 1. So since 1 is connected to 2, 1 should come before 2, and 2 should come before 3, and then 3 should come before 1, right? So if 3 is coming before 1, and 1 is coming before 2, and 2 should come before 3, but we can see that 2 is coming after 3. So there is again a contradiction. Okay. So, Sumit, I was asking that why it is necessary to have a directed as well as an acyclic graph while we were dealing with topological sort. Okay, this was a question, Sumit. Okay, so I just mentioned why. So let us move to the algorithm part. So first we will be doing a DFS algorithm. Okay. Hmm. Okay. Now, why DFS algorithm? And I will be showing you how both the algorithms will work. First, we will show by DFS. So, what a DFS algorithm does here is that it basically keeps on going to its depth. So, if this node, let's say we are starting a DFS for 5, 5 will go to 2, 2 will go to 3, 3 will go to 1. Okay. DFS will basically keep on calling itself as long as it is able to go to the depth of our graph. Okay. Now, but the thing is that we have to find a valid order. How we will do that? Okay, this is the concept. How we will do that? Okay, so what we will do here is that we will maintain a stack. Okay, a stack data structure. And in that stack data structure, as we know, stack is a kind of a data structure. If whatever elements are coming inside it, if it is coming first, it will come out last. Okay, it is a LIFO kind of data structure, last and first out. So whatever elements are going inside it last, it will come out fast. First, okay. So this stack will help us keep an order. Why? So basically what we will do, the way we are processing our DFS, we will put those elements in the stack. For example, let's say we are starting with element number 5. Okay. So what it will do, it will keep on going DFS. And as long as it will keep on going DFS, let's say 5 will go to 2, 2 will go to 3, 3 will go to 1. And from 1, it sees that it is not able to go anywhere. So it will put 1 in DFS. Now again, I will come back to 3. And from 3, it will return to 3, it will return to 2, it will return to 5. It will go to 0. Okay, so give me a minute, please. Just give me 1 minute. Node will have many integers. Yes, Sumit, you are correct there. Okay, so let me open the problem statement also and the yeah. So first we will solve using DFS and then we will try to solve using BFS. Okay, so let's look into it. Yeah. So basically, what exactly the algorithm is says that we will traverse all the components of our graph. So the first point is that we will traverse all the components of the graph. Okay, all the components of the graph. And since we are traversing all the components of the graph, we will keep a visited array as well, which will be initially initialized to 0. And we'll also maintain a stack data structure where we are going to store the nodes after completing the DFS call. The most important part here is that we will only store the node in our stack after the DFS call gets completed. After DFS call gets completed. Okay. So all the components of the graph. Okay. Now what we will do, we'll make sure to carry a visited array. Okay, which are initialized to 0. Okay. Now as we are calling the DFS array, we'll just make it visited as per the rules of DFS. Okay. So we are calling the DFS node. Let's say we are calling it for 5. We are marking 5 as visited. Okay. Then DFS call is made to its adjacent node. Then 5 will call 2, 2 will call 3, and so on. It will occur. Now after visiting all its adjacent node, DFS will backtrack to the previous node, and meanwhile the current node is pushed into the stack. So as it will come to 1, it will see that it cannot no longer visit. Okay. So basically, it will just put 1 inside the stack. Okay. Now after that, what will happen? So it will backtrack to node 3, and you can see that when it will backtrack to node 3, it can again put up 3 inside the stack. Okay. So this is how the stuff will work. Okay. So this is how the DFS algorithm will work. Let us do a dry run of it as well. Okay. Okay. So one more thing here is that let us basically do a dry run, but with let me just clear this graph and let me do a dry run with this. I'm drawing the graph again. Okay, we will do a dry run of our DFS algorithm, and then we will proceed further. So let's say this is 5, this is 0. Okay, and this is 4, this is 2, this is 2, this is 3, this is 1. Okay, so 5 is connected to port 0, 4 to 0, 5 to 2, 2 to 3, and 3 to 1, and 4 to 1. So since we will traverse across starting from 0 till 5, so basically initially we will go to 0. But as we will go to 0, we see that we are marking 0 as visited. Okay, so let's say this is our visited array: 0, 1, 2, 3, 4, 5. Okay, so yeah, so we are marking 0 as visited. Okay, so since we're marking it as visited, now we will call DFS for our 0. Okay, so we will call DFS for our 0. It will call for 0, but it sees that it is not able to go to its adjacent node because 0 doesn't have any adjacent node. In that case, it will push 0 into the stack. Okay, so our stack will look something like this. Then we will go for calling 1. Okay, now again it will go to 1. Now 1 will be called as 1. It will mark 1 as visited, but also 1 doesn't have any adjacent node. So 1 will again be pushed into the stack, and the DFS is done. Again we will call for node number 2. Now we see that node number 2 will be marked as visited. Now node number 2 will call its adjacent node, which is node number 3. So it will mark node number 3 as also visited. Then node number 3 will call its adjacent node number 1, which has already been visited in that case. Okay, so in that case what will happen, it will push 3 into the stack, and after it will backtrack to 2, and it will put 2 into the stack as well, because 2 and 3 is done. Okay, why we are doing that? Basically because since 2 and 3 are connected, 2 should appear before 3, and inside the stack it is appearing after 3. So that is the reason, because once we will take it out from stack, it will be in the correct order. Okay, so this is done now. After that, what will happen, DFS call will start from node number 4. So we'll mark node number 4 as visited. Now 4 has two adjacent nodes, 0 and 1. Okay. So it will find all its adjacent nodes 0 and 1 have been previously visited. Now we see that 0, 1 and 1 has been previously visited. So now node number 4 doesn't have any nodes to visit. So it will push itself into the stack, and the DFS is over. After that, we'll come to node number 5. We will mark it as visited, and we again see that node number 5 also has no adjacent node that it can visit. So it will put 5 also. Okay, inside the stack. So I hope everyone got this. Now what will happen, basically, let me just erase this part. Yeah. So now what will happen basically is that we will pop all the elements one by one from the stack. So we see that now my answer will be 542310. 542310. Okay. Why this will be the answer? Because as you can see that 5 is connected to 2, so 5 is appearing before 2. And what exactly is the intuition behind this? The intuition behind this is such that since whenever we are pushing into the stack, we are only pushing into the stack, we are only pushing an element inside the stack when basically we cannot find any element that it can do a DFS with. When there are no adjacent element to any given element, we are pushing inside the stack. So what does this mean? It means that basically that node is not directly connected to any other node. Okay, so that if that node is not directly connected to any other node, it means that that should come after all the nodes. So that is the reason we are pushing in the stack. And once we're taking it out, it will come before all the nodes. So 5 will come before 4, 2, 3, 1, 0. Okay. 5 will come before 3 because 5 is connected to 2 and 2 is connected to 3. That is why 2 is coming before 3. So this is the reason we were using stack. Okay. So let us move to the coding part. I hope everyone understood the intuition behind the DFS. Okay, so the first and the most important thing is to make a visited array, which I will tell you. So this is the GFG practice question. So the first thing is to create a visited array. Okay. To create a visited array. Okay. And at the same time, we'll also create a stack. Now the thing is that we will do a traversal for all the nodes, all of our given nodes. Then what we will do? We will check whether that node is visited or not. If it is not visited, then we will call DFS for the given node. Okay. We will call the DFS for the given node. Okay. Now what will it do? Basically, we have to implement this DFS function. Okay. Now let us see how we will implement the DFS function. Now, the most important part in implementing the DFS function was that once the DFS will end, we have to basically push the node into the stack. Okay. So that was the most important part while we were doing the DFS. Okay, so this is a DFS. This DFS will accept a node from where the DFS should start. Okay, first of all, it will mark that node as visited. Then it will go across all its adjacent node. And if that adjacent node is not visited, in that case, it will again mark DFS. Now, once it comes out of this for loop, it means that there are no adjacent node to visit. Whatever node we are at, we will just push into the stack. Okay, because that will be my topological ordering. Once I am basically removing all the elements of the stack it will become my valid topological ordering. And finally, we will remove all the elements from the stacks. We will initially take the top element and then we pop it out. So basically, whatever element will go out at the last will become the first element of our order. So this is how we are basically applying according to the concept of topological sorting. So let us submit this problem and see whether it is correct or not. Yeah, so as you can see that this question is correct. All the test cases are passed. So therefore, I hope everyone understood the concept. So let's move to the next part then. Topological sort is there. If do you have any doubt in topological sort, you can kindly ask me. Any doubts, or should we move to the next topic? Okay. So now one homework I will give it to you is the concept of Khan's algorithm. Okay. So okay. Lokesh is saying please move on. Okay. So we are already on short of time. So do you want me to discuss Khan's algorithm or would you like to have it as a homework? So let's see. So Khan's algorithm is also a type of algorithm which will help us write a valid topological order for a topological sorting order for any given graph. Okay. Now this Khan's algorithm is based on BFS. Okay. Now what algorithm I just showed you was a DFS algorithm, but this time I will be showing you a BFS algorithm. Okay. So let's see. Okay. So how exactly will this work? Any ideas? Can anyone write up briefly how exactly this Khan's algorithm works? Okay, Lokesh says he has no idea. That's okay then. Let me explain it to you how it will work. So the first step involved is to find the in degree. Okay. Now what exactly is in degree we have to see. Okay. Let I will explain it to you later what exactly is in degree. So in degree basically means the count of nodes which basically are terminating at any given node. For example, let's say I have a node U and a node V and it is connected in this fashion. So we can say the in degree of V is equal to 1 because one node is connected. U is connected to V, so the in degree of V is 1. So whatever nodes is coming inside V, it will increase the count of in degree. Okay. So first we will calculate all the in degrees. Okay. Then what we will do, we'll put a data structure. That data structure will be a queue data structure because we are applying a BFS kind of algorithm. Okay. Now what we will do, we will push all those vertex inside our queue which have an in degree of 0. Now can anyone tell me what does an in degree 0 means? In degree 0 means a given node, all other nodes are ending in this node. Okay. So all other nodes are ending in this node. Okay, so it means that since let's say in our topological sorting, since if any node which is such a way that its n degree is equal to 0, all of the nodes are ending in that 0, it makes sense that I should keep this node to the end of topological sort because all other nodes are ending in this node and these nodes should be present before these nodes. Okay, so the nodes which are basically ending into this node should be present before the node itself. So that is the reason if the in degree of the node is equal to 0, we will push it into our queue data structure. Okay. So after what we will do, we will run a BFS algorithm. We will take that element from our queue. Okay. So we will push it into our queue. Now what we will do? So now what we will do? We will take this element from our queue. Now we will go to its all adjacent nodes and we will decrease the node by in degree by 1. Okay. So basically what we will do, we will decrease the in degree by 1 of all the nodes which are connected to it. So in that case, what we will do, we will basically taking care of this. Now we should take care of the other nodes as well. Now what we will do, we will check whether if there are any elements such that its in degree becomes 0. If their in degree becomes 0, we will push it into the queue. Okay. Now the thing is that whenever an in degree will become 0, it means that it has got its place in the topological sort. Okay. Because there are no elements to which it is connected. So there are no elements in which no elements to which we should keep this present node before that. Okay. So that is the reason we will try to keep our in degree as equal to 0. And as soon as we are getting that in degree equal to 0, we will push it into the queue to make it the further in degrees equal to 0. And finally, what will happen when the BFS will be over, all the in degrees will become 0. Okay. Because we are basically reducing our in degree at every steps. Okay. So this is how BFS algorithm works to find the in degree of our to find the topological sort. Okay. So I have explained you the concept of how we can basically apply the in degree. So I will just give you a pseudo code also, and this will be your homework to basically implement the Khan's algorithm. Okay. Now I am writing all the step-by-step approach of how you can solve this. Okay. Just give me 2 minutes. Yeah. So the first thing that you should do here is that first you will be declaring an in degree vector. Okay. The first you will be declaring an in degree vector v, which you will mark it as 0. Then what you will do, you will make this in degree. You will basically add all the in degrees. How we will do that? We will run a for loop for I equal to 0 to v all the vertices. And then you will basically go across all its adjacent element auto it in adg of I. Okay. And you will in degree plus plus, you will do this. So this will basically calculate the in degrees. Now what you will do, you will again run a for loop and check if the in degree is equal to 0. If it is equal to 0, you will push it into the queue. Okay. I hope this part is done. Calculate the in degrees, and if the in degree is equal to 0, push it into the in degree. Okay. I hope this part is clear to everyone. Lokesh, is it clear to you? So what will happen now? Now we will run our BFS algorithm. Okay. Now how exactly we will do that? We will declare, we already have our queue data structure which contains n degree equal to 0. We will declare a vector answer in which we will store our topo sort. We will run a while loop. And this while loop will continue as long as our queue is not empty. we will take the node from our queue. Okay, and we will pop that node. Now what we will do, we will push that node into our answer vector. Okay, we will push that node into our answer vector. After we push that node into our answer vector, we will go auto IT in all the adjacent nodes of the given node. Then what will I do? I will decrease the in degree. Okay, I will decrease the in degree. And if the in degree is become 0, if the in degree is becoming 0, I will push that again for further exploration by the BFS algorithm. So this will basically help me fill up my answer vector. Okay, so this is my answer vector, and as soon as I'm popping from my queue, I will just put it into my this. And finally, this vector will basically give me a valid topological sorting, and I will return this vector. Okay, so this is the concept of topological sorting, and I will request everyone to kindly solve this problem on the Geeks for Geeks platform. And so therefore, this brings us to an end of session. So if you have any doubts, you can ask me. Yeah, thank you, Lokesh. So we have proceeded to the end of our problem session. So I would give you a small information about how exactly is our series. So basically, we meet at every alternate day at 10 p.m. onwards to discuss concepts and questions related to graphs and trees. Okay. So and if you are preparing for your interviews, upcoming internships or placements, you can basically watch this series. And was the sixth session. From next, we will be for continuing with our session further. Every alternate day, you have to join this session. Okay. So this will continue for the entire month of December until the first week of January. Okay. I hope everyone will enjoy this session, and we will be covering all the topics that are important for the interview point of view. This will help you prepare for the interviews. Okay. So if that's the this is from my side, then if you all do not have any questions, then we can basically wrap this session up. Thanks a lot for your joining. Thanks, Sumit, for consistently staying in this session. I wish you all the best. Thank you, Lokesh, for listening to me. And thank you all the other people who were there with me in this session. Okay. So see you day after tomorrow then. Bye bye. Have a nice day ahead. Or in fact, good night. Bye.